Well, for part 2, write equations and use ICF tables. That's the best way to do these kind of questions. Okay. Okay, write the equation further, then you write an ICF table in terms of moles can be done, and the working will be a lot more concise, right? Right, we have about 5 minutes left, just for this one. Whenever you are done with part A, right, you can try the other worksheet though, right? The other worksheet, I'm just going to try one question. Okay, about 2.5 minutes left. And just 2 minutes left. Huh? Yeah, I think more or less you guys are there already. Okay. Anyone needs more time? Or I can just go through now. Yeah, I think I'll just go through now. You see some of you guys start already. Okay, so come. Take a look, right? Okay, for this question, the amount of working that you need to do is very little. Okay, I can tell you that first. Okay, that's why I encourage you guys to write all your answers in the ICF table. It's very concise. But first of all, you need to understand first part. Right? Okay, first part leads to your second part, right? Okay, they have both of these species. So you should recognize that it's a buffer. Right? I have this first species, this second species here. They are in some sort of proportion. And then you add OH minus. Okay, so what does OH minus react with? It has to react with the acid, right? Not the base. Okay, so go and take your acid and just add your OH minus. Remember, this is neutralization, so pull arrow. You form a little bit more of that base. Okay, and then water. Okay, so that's your answer for part 1. But you have to copy out this equation for part 2 also, because we are going to be using this to write out our ICF table. Okay, so I just straight away go to part 2. Okay, initial, change, and final. This is the best way to plot your values because I have a lot of values here, right? Okay, so first thing I'm going to do, I'm going to convert every single thing there, right, into moles. Okay, they give us volume, concentration, just convert everything first. Okay, so the acid initially, right, okay, they gave us 0.001 moles, right? Okay, that is how much acid was added. How much base was added, they also gave a certain value, right? I just convert 0015. Okay, again, I don't care about water. Okay, so those are the initial amounts. But then now I'm adding KOH. KOH, they added 14 cm3, which I convert first, it will be 0.0014. Okay, so just place these 3 values onto your table first. And what do you notice? Okay, based on these values they added, what do you notice here? Very important idea before you can move on. You must identify the limiting reagent, right? Which in this case is who? The limiting reagent is the lower value, right? Which is this guy over here. And usually this is a bit weird because usually the limiting reagent has to be your strong base, right? But never mind, okay, just follow whatever the question says. You get limiting reagent, you minus it off, minus on the left, plus on the right. So what I'm going to have now is that I have a lot of base. I have very little strong base left, but the thing is I do not have any more acid. So what's going to happen here? Okay, I now have strong base and conjugate base. Is this a buffer first? Okay, it's not a buffer, right? Okay, so are we going to deviate away from the buffer idea? No, because I hope you all realize something. The unreacted NaOH can further deprotonate this species. Can you see that? This species is diprotic, so it can deprotonate one more time because of the fact that you have unreacted OH minus. So in other words, I need you guys to write down a second equation. Currently, I only have this first conjugate base, but then I have a bit more OH minus remaining, which they can react together to form the second conjugate base, the most deprotonated form. So in other words, okay, there will be a second equation happening here. You shouldn't stop over here because this OH minus can react further with this guy. So I'll come out with this equation and I'll come out with a second ICF table. So go and look at how I place the values. This value here is going to now be the initial amount, and my OH minus is this value here. Okay, I don't have any of the second conjugate base, so it's 0. Okay, water you just ignore. And again, right now your job is to yet again do the same thing. Okay, identify the limiting reagent. You can see that now the strong base is a limiting reagent. Minus it off on the left, minus it off on the left, and plus on the right. Okay, so let's just fill in our table. Here is 0, here is 21. So as you can see, guys, now is this a buffer? Now that everything has settled, all the dust has settled, is this a buffer equation, a buffer reaction? It is, okay, because now I have a conjugate acid and a conjugate base pair. It's just not the pair that we started off with. Can see that? We have gone past the first pair, and then now we are end up with the 2 other pairs over here. So that's the idea behind this question. Okay, it has 2 reactions happening to get a different pair of species for the buffer. Then what do we do now? Okay, in order to find the pH of this buffer, very simple, right? Okay, just take out your buffer equation. Okay, what's the equation here? pH equals to pKa 1 or 2, by the way. 1 or 2. Now it's 2, right? Okay, because you look, the 2 species over here belongs to the second equation. Okay, so you should be using pK2 plus log conjugate base over acid. So go and look at conjugate base over acid.
Okay, you are looking at these two pairs here. Okay, so look at who's the acid and who's the conjugate base in this case. Now you just need to submit the values. pK2 is already given to us. Second conjugate base is 0.0004, 0.0021. Remember to divide by V on both the top and the bottom because you are calculating in concentration. Okay, and then we can get our final answer 3.56. That's the answer to this buffer.
Yes. Why doesn't the second acid like dissociate by itself?
No, it has to have a base to dissociate. Okay, when you add strong base, it will suppress the dissociation, the natural dissociation. It only dissociates by itself if it's left alone. But now you have something, right, to force it to dissociate in an acid-base reaction.
But if it's after it fully dissociates, wouldn't it try to dissociate by itself?
Okay, you have to realize buffer, right? Okay, very important idea, guys. Buffer, no dissociation. You should segregate both ideas. Buffer is just acid-base neutralization reactions. The buffer has no dissociation. The reason is because, right, why is there no dissociation in a buffer? A buffer contains very large excess of the acid and conjugate base. And if both sides have very large excess, you will basically just not shift the position of equilibrium. It will suppress the dissociation. It cannot proceed on either the left or the right because both sides have very large excess. So you should never ever conflate dissociation and buffer together. A buffer should only just be acid-base reactions. Okay, let's just keep it like that, right?
In this case, is there like acid much more in excess than the conjugate?
Not really. 21, 4. Okay, this guy is a lot more, about 5 times more.
So wouldn't like it.
Okay, but when we say large excess, it's in large excess compared to whatever OH minus or H plus that you add externally. Okay. Can see this question now. The next time buffer, right? You can see just mole ratios. Okay, limiting ratio and all that. As long as you craft the correct equation, as long as you plot the correct table, you can get the answer very quickly. There's no working involved in this. They're just tables. Okay. Now with that said, right? Okay, we're gonna move on to part B of this question. Okay, part B is made out of 3 parts. I'll give you guys about that amount of time also. This is about KSP. It's slightly challenging, okay, but if not, I think it's generally okay, doable. Okay, so I want you guys to look at this question. I'll give you guys a bit more time for this. Okay, maybe about same thing, about 8 minutes now, I think. Okay, 9 minutes, 9 minutes. Okay, 9 minutes for 6 marks. Right? So that's for 1B. Okay, that very fat paragraph over there, right? The most important part is the purpose. You look at the last sentence, that's the most important part in that big fat paragraph. Okay, read that carefully. Okay, the purpose is to blah blah blah. Okay. It says something about maximum amount or whatever. That part, very important.
We've got 4 minutes left now, right? You should at least be at part 2 right now. Okay, part 1 cannot do is fine, it's only 1 mark, right? Okay, for part 3, they ask you use what data, you just use those data. Whatever the question asks you to use, is all you need to use. Okay. So just follow the question now. Yeah, I'll give you guys more time for this, right? So you have about 4 minutes left. It is after extra time. So most of you guys are at part 3. Gentle reminder again. Just follow the 2 things that the question asks you to refer to. Okay, the table 4.1. Follow whatever, take up the data from there. And the answer in the previous part also. Okay, that's all you need to solve this question. Okay. Okay, 1 final minute. Okay, those who got your part 3 answer, the answer looks weird, but it's correct. It looks weird. Okay. Right, okay, time's up. Okay, so I give you guys enough time to try this. Okay, so come, some comments on this question. I think it's a very well set question. I don't think it's overtly difficult. I think it's actually quite in the A-level difficulty range if they decide to make it more on the challenging side. Okay, so let's take a look. Again, I first highlighted this clue here. Okay, this is the main purpose of this question. They tell you guys what they want to precipitate. What does this statement mean? If they say Ce3 plus is precipitated, okay, so they say it's contaminated with these 2 ions, right? But if they only want to precipitate Ce3 plus, it implies that this salt is the only guy that precipitates, right? And it has to be the first to precipitate. Okay, the second to precipitate will be the other one, which you don't want to precipitate this because it's selective precipitation. Right? In selective precipitation, you only want to precipitate 1 ion, but the other guy is left in the solution. So that brings us to later part 2, right? Okay, so we can take a look at this diagram first. As you add more and more C2O42 minus, okay, you will have 2 different key features. Here is the minimum concentration to precipitate the cerium salt, right? Because this is the guy that precipitates first. The guy that precipitates second is your calcium. So it requires a much higher concentration to precipitate here. So we'll discuss that, right? Okay, in part 2. Okay, but you kind of need this diagram to really visualize this a bit more clearly. As you can see, this is the start of the experiment. The start where it begins precipitating. If you add anything below that, right, nothing's going to happen. So you're not going to start anything, right? Okay, but where do you end? Where does the reaction end over here? Where does it stop? Or does it just go on forever and ever? At what point on this graph here, right, okay, does the reaction stop?
Okay, it ends off over here, right before this point, right? Because this is the point where you're going to precipitate the other salt, and you do not want that to happen, right? If you want to avoid that from happening, you have to make sure you just add just enough, okay, or just before that amount, okay, that concentration, so that it doesn't precipitate out. Okay, and that idea that's going to lead us to our calculations in part 2. But let's look at part 1 first, okay? How do we prove part 1? They ask us to prove the KSP of this reaction just by using this data in the table. Okay, so you'll focus on the first one because that's obviously what I'm concerned about. You have to ask yourself what this K represents. Okay, if you convert the log K to just K, right? K represents what? It's just the KC, right? A normal KC, right? Okay, you take your products over reactants. Okay, so why not, right? Let's just find this K first. This K is products over reactants. How do you write it for this? Do we take this product? No, okay, because this is a solid. So essentially, it's just 1 over the reactants. The reactants are aqueous, so you have calcium 2 plus and C2O4 2 minus. Okay, take note, guys. I am not doing anything. I'm not even thinking right now. I am just asking myself what K represents. And you have to write this out because this is a show question. Okay, after you've written this out, I'm just gonna convert 8.63 to the actual number. So it's 10 to the power of 8.63. Don't put a minus there. I think some of you guys are happy put a minus there. It is just math for here. Okay, about what they want us to find. Okay, they want us to find KSP. Okay, guys, how do you write the KSP of this salt? KSP is just the product of the ions, right? Okay, so the ions over here are just calcium 2 plus and C2O4 2 minus. Guys, how do we use the previous data, right, to find this? What's the relationship? Reciprocal, right? Okay, it's just a reciprocal of one another. So what you guys need to write here is that it's equal to 1 over K. Okay, that's how you would link up both relationships. And then you can write down your answer. This is 1 over 10 to the power of 8.63. And then you can get your final answer here, which is, what is it? 2.34 times 10 to the power minus 9. Then you can claim that this is shown. Okay, again, right? Okay, you're supposed to write down both K and KSP, and then you can link up with 1 over K. Can see that? Okay, I'm just manipulating. Okay, so how do I get all this up? It's just to write down whatever you are given and write down whatever you are asked to find. 2 things. Whatever you are given and whatever you are asked to find. Write these 2 things out there, you can see. If you don't write anything out, you won't be able to see anything. So guys, in exam, right, just write whatever you can find first. Okay. Now, moving on to part 2, that's where the selective precipitation process begins. And they only want you guys to find the minimum concentration needed. Guys, to find the minimum concentration, what expression do I use? What is the minimum condition to precipitate something, anything? IP equals to KSP, right? So all you need to do over here is just take IP equals to KSP for both salts, and then you get 2 answers. That's it. Okay, this one really cannot get this wrong. Okay, you shouldn't be spending too much time over here also. Okay, IP equals to, okay, I'll find calcium first. And this is equal to its KSP, which you found just now at the bottom here. Go and find the concentration of C2O4. This is the minimum to precipitate calcium oxalate. I think that's what it is. Okay, so go and find this. Okay, go and divide. Okay, the calcium 2 plus is already given to us. So go and divide by 0.01. Then you can get this as your concentration. Okay, so that's one answer. Now the second one just need to square root or cube root or whatever, right? Okay, so just be careful with that. The next one is IP equals to cerium 3 plus square and then C2O4 2 minus cube. Okay, just be careful with that. I think it's 6 point something, right? Okay, 6.6 times 10 to the power of negative 31. The math you're going to do yourself. Okay, cerium 3 plus also the same concentration. You divide by this square and then you cube root the thing. Okay, so I can find the minimum concentration. Again, go and write this clearly to precipitate this salt. Okay, so then your answer over here is definitely have to be much lower. Okay, 1.88 times 10 to the power of minus 9. The value here has to be lower because yet again, from what the question has told us, this is the guy that precipitates first. And the one that precipitates first has the lower minimum concentration, which makes sense if you look at the table there. Okay, in other questions in future, they might ask you to find the minimum concentration first, and then you are asked who precipitates first. It's always the smaller concentration that precipitates first. You should know that by now. This question tells you already then Okay, you are using your answers to confirm. Okay, can? It is part 3 that some of you guys are struggling with. Okay, but any issues with part 2? Concept-wise, I think part 2 is really nothing. Okay, let's look at part 3. So they are saying that this question is a bit weird. Okay, usually you add the C2042 minus, you add manually to precipitate selectively, right? But now this C2042 minus, they say, is being contributed by oxalic acid. You can see that they did tell us that there is actually oxalic acid swimming around in this solution also. So they're asking us what pH, right, will precipitate the maximum. Okay, go and highlight those last few words. Precipitate the max amount of Ce3 plus. Okay, so guys, go and write this in your answer also. To precipitate the max Ce3 plus, what do I need to do here? Okay, what point on this little graph over here are we at? The max amount. How do you precipitate the max? It has to be at the end point, right? You're supposed to add this concentration so that you precipitate the max. You don't add at the start because you only precipitate a bit. You add, this is the maximum you can go. You can't go anywhere beyond this, correct? So what is the concentration of C2042 minus at this point? Is whatever to precipitate C calcium, this value over here. So let's just write that down once again. To precipitate the max concentration, C2042 minus must be this value. Don't take the other value. So this is the answer that they want us to take from D part 2. You see, there are only 2 things they ask you. This is one thing already. Can you see that first? Okay, concept-wise, you should know this. To precipitate the max amount, you must be at the end point. Okay, so take that concentration. Next, what data from table 2.1? They want us to find the pH. And if you look at the table from this thing here, pH, H plus can only come from this third equation. So logically, go and pick out the third equation. Okay, and this third equation, they also gave us a Kc value. Okay, so let's just write that out. Okay, the Kc of this is just products over reactants. Just write it out. Okay, the question asks you to take data from here, then just copy. Okay, so I'm just going to write products over reactants. They ask us how much H plus, how much pH, right? So they want to find the H plus lah. That means you need to have everything else. Okay, do I have K? Yes, I have K. K is 10 to the power of negative 5.06. Here got negative because they gave us. Okay, then your C2042 minus this value over here. This one is 1 mole per dm cube. Just sub everything and you get the answer already. Okay, so over here, okay, I want to find H plus square. C2042 minus is this value. Okay, and this one is 1. Then the power of negative 5.06. Okay, go and solve for H plus. And then solve for pH. Okay, so you notice something, guys. Okay, I want to highlight one thing over here. Once you calculate H plus, you realize that the concentration of H plus is very, very high. 6.1 mole per dm cube. If you put negative log into the calculator, you will get negative 0.785. That is the answer. Okay, and that has thrown a lot of people off in the actual exam for Nanyang, right? Okay, you do doubt your answer, right? Because you never really seen negative pH before. But guys, it's just math. Okay, let me just highlight this. In the A levels, if you get a negative pH, don't doubt yourself and say, oh shit, did I do something wrong? No, you don't do anything wrong here. Okay, when does pH give you a negative value? By math, anything above 1 mole per dm cube of H plus will give you a negative pH. You don't believe, you're going to type into the calculator. Do an experiment for yourself. Okay, so negative pH exists. Okay, it's not mathematically wrong. Okay, anything above 1, we just very rarely deal with very high concentrations of H plus. That's why you guys are not used to it. Okay, so just be very careful. Okay, most of our H plus is less than 1. That's our numbers are pH always positive. Okay, negative pH possible. Okay. It's up, right? Okay, so I think this is a very well set question. Go back and try this one more time. The whole thing, including the first part. All right? Any questions? Okay, so with that said, okay, let's just move on to the next question. Next question is generally quite okay. Okay, can you guys look at question 2? Okay, and just do part A. Part A is made out of 4 parts. We settle that first before we move on later. Okay, later on, I still want to use the other set that I gave you guys. I want to go through one question from there too. Okay, but anyways, do 2A. This one not much calculation, so I'm not going to give you guys that much time. Okay, about 8 minutes will do. Right, 8 minutes 2A.
The bare minimum is to be able to do part 2 and part 3, right? Okay, 5 minutes left also. Yes, A part 1 to part 4. Yeah. In the atom economy, the part 1, right? Okay, you got to make sure that the value that you get is relatively high. Because after all, they did say that this is an environmentally friendly reaction. So use that to check your answer. If your answer is like very low proportion, right, then probably wrong. Right? Okay. Okay. The 2 plus is 0.01. The KSP you have right. 2 minutes. About 1 minute left. Okay, and let's just go through the answers. Okay, part 1 and part 4 talks about this idea called atom economy. Okay, it's good to be exposed to a lot of these funky concepts, right? Okay, so that you never know, maybe the A-level paper, right? They come out with one question, right? That atom economy also, because it's quite a thing now, right? Okay, environmentally friendly and whatnot. Okay, so yeah, okay, so this is a measurement, right? Okay, of how much waste you have incurred in a reaction. Because a lot of the times when you synthesize things, right, you'll lose things as byproducts. Like you lose water, you lose this, you lose that. If you lose a lot of things, then that's a very wastage, a very high wastage reaction. If you take a look at this reaction here, your answer should be relatively reasonable, like high enough. Because they say a high atom economy is something that's friendly, which they said it is, this reaction here. Okay, so I think, right, the definition of atom economy there, right, is not very clear. Yeah, I think they also never really said it to be very clear there. Molar mass of desired product, I'm sure everyone can get this, right? Okay, because your ibuprofen is your desired product and it is 206. Okay, this one should be fine. Okay, but then you go and divide every other product, because when they say all products, right, I think some of you guys like added all 3 products together. That's not true. Okay, the product that we are going for is actually just your ethanoic acid. Because if you realize something, guys, your desired product, ibuprofen, is made from all these intermediates. So all these intermediates, right, are leading up to the desired product. They are not external products. Can you see that these 3 guys are effectively the same thing, right? Okay, so that is your desired product, but this is your undesired product. In other words, this is the waste that has incurred in the process. So that's why, right, you are meant to just account for ethanoic acid, which has an MR of 60, meaning to say, the total products that you have, right, is both your ibuprofen and the wastage that you have incurred, which is just the ethanoic acid. So that's pretty much it, right? Okay, and then when you calculate this as your answer, 0.774. Relatively good, okay, meaning about 77% efficiency, you can interpret it that way. That means about 22%, 23% has been incurred as wastage, which is considered high, okay, according to this question. Okay, now part 2 was the answer. What reaction is this? Okay, E sub, okay, electro sub. Okay, step 1 is just a reaction that happens on the benzene ring. Okay, benzene ring, you substitute the H, it can only mean electrophilic sub. Okay, let's just move on from that. Okay, part 3, distinguishing test, not difficult. Again, right, I need you guys to just identify all the possible answers. I think there are like 3 answers here. Okay, come. List down what I'm not going to care about observations, that one you're going to settle yourself. Okay, what are the answers we can use here? Between A and ibuprofen, what can we use? NaHCO3, okay, or just sodium carbonate, right? Okay, because it distinguishes your carboxylic acid. Anything else? I have 2 more now. Okay, iodoform, good. Okay, iodoform test, can they distinguish your compound A? Because A got methyl alcohol. Okay, last one. Mild oxidation. Okay, mild oxidation, right, is your alkene become diol. Don't use the word mild oxidation very loosely. Common mistake. I think what you meant is controlled oxidation, right? Using what? K2Cr2O7. Okay, don't call this mild oxidation from now on. Mild oxidation is referring to this scenario only. Okay, this K2Cr2O7, yeah, I get what you mean, is controlled oxidation. Okay, but you don't actually need to control this one, okay? Because you only need to control oxidation if you're forming an aldehyde. Okay, but this is a secondary key alcohol, you turn into a ketone. Why can't we use KMnO4? That's the question. Okay, both will react. Okay, so take note, you can't use KMnO4 because of side chain oxidation. Both of them have side chains, must be very careful here. If you use KMnO4 wrong. Okay? PCl5 will react both them. This one will become acyl chloride. This one will become chloroalkane. Both can. Yeah. So both will react over. Okay. Part 4. Right. Part 4 is another atom economy question. Okay, so let's just read what the question is saying. This ethanolic anhydride, this weird thing over here, can be recycled. So you just imagine first, regenerated, recycled, whatever. The atom economy is going to go higher or lower? Higher, right? Okay, it's going to become more environmentally friendly because you are recycling things. Okay, they are saying, right, you can regenerate this using your wastage, right? You can take your waste and convert it into something useful. Of course, it's going to become higher. Okay, so expect your answer to be higher, of course.
Okay, but first of all, they did mention, right, you need 2 ethanoic acid to produce one, okay, you regenerate the ethanolic anhydride, and then there's water. Okay, this is what the question told me. Okay, so what's gonna be the new atom economy now? New atom economy. Okay, so our desired product is still this, it's still 206, but now divide by 1. Okay, so now is the wastage these two? What's the wastage actually? Is this waste? It's not waste, right? We are actually using this for the reaction. So it's useful, not waste, right? Okay, so this is the waste. Okay, water is the waste. So what do we do here? 206 plus 9, not 18. Okay, why 9? Because just be careful here. They say you need 2 ethanoic acid to produce 1 water. So based on this pathway, 1 ethanoic acid can only produce half of water. So you need plus 9. Okay, then the answer here should be a lot higher. I think it's like 90% or something. Okay, 958. Clearly, you are improving the efficiency of this experiment. Okay, can so just know what atom economy is. You never know, maybe A level will come out. Okay, is all these are not products, these are your desired products, so don't go and count them separately. Okay, just look at the final compound. Wastage is everything other than that. Okay, all good? Okay, so let's move on to part B, mechanism drawing. Okay, this one again never difficult one. Just follow instructions and you will never struggle with this. Okay, do B part 1 to part 3. These 3 parts are not hard. Okay, can go on. Right? So take about 10 minutes. To be more than enough time. Okay, 2B.
Oh, wait, sorry, question.
Your ibuprofen should be 206, not 208. I think you calculated wrongly. And yeah, we can't use PCl5 just because carboxylic acid will also react with PCl5. Your ibuprofen, just go and count again. I think it should be. And now you can see that I got C13H18O2. I didn't get 20H. You can count again. you're going to check your charges whether they're balanced. See some of your steps, the charges not balanced. If you finally, you don't have to arm yourself, you never know what they want. But yes, because it's like, yeah, I know what you mean, pretty sure. But we did say the value is here, that's it. So in other means affects the value. That's what I thought. Because I thought like the one CO minus cancel from you. This is what you usually goes. Because we have three balances on. So we want to see our minus at end also three balances on. We have 3 minutes left. And let's still part 2 and part 3. Okay, part 3 especially easier, like really can be done. We give a lot of marks for that. So. Yeah, by the way, if you are part 3, I think the ibuprofen got cut out, so just be careful with the structure. The ibuprofen is a carboxylic acid. The printing messed up. Okay, we have 2 minutes. Remember, try to settle your part 3 also. Suggest question. So consider what the bond form first. How does that relate to a complete reaction? There's a lot of things you need to build in. Look at the overall reaction. Okay, for part 2, okay, they ask for consider the bonds form. You're going to look at what's the most significant bond that's formed, right? Okay, that will contribute to a complete reaction. That means this reaction is very favorable, very spontaneous, something like that. Okay, so think along those lines. How could a bond form contribute to a very favorable reaction? Okay, something along the lines of energetics, really, because they say it's bond forming. Right, energetics. How does that relate to favorable reactions? Okay, so those are the clues I'm giving out already. Right, just perhaps try something, whatever you can think of. Right. Okay, and time's up. Right, okay, again, our focus here is part 1 and part 3. Part 3 synthesis, very simple. Okay, but part 1 mechanism also can be simple if you follow the instructions carefully. Okay, let's look at step 1. Okay, draw everything out first. Okay, then you need to draw your intermediate. Okay, go and read the question. They say the oxygen's lone pair, which is rich, attacks the phosphorus, which is poor. Okay, so perhaps you can put in your partial charges to ensure that phosphorus is poor also. Okay, then afterwards you want to break one of these bonds and give it to chlorine, because that's what the question said. You form a Cl minus ion, alright? Okay, so let's just follow suit. Okay, over here, the OH is still there. And take note, guys, I see some of you are forgetting the positive charge already. Oxygen is giving away electrons, right? Giving away electrons will get you a positive charge. And now he's bonded to phosphorus with 4 chlorines. I'm just going to put Cl4 over here. Okay, phosphorus has 5 bonds. You form the 6th bond, then you broke the 5th bond. Eventually, it still has 5 bonds. That's why phosphorus has no charges. Okay, and then you get Cl minus. From there, okay, let's just bring this intermediate to the step 2. Okay, now just follow step 2. I think step 2 also makes it very clear. They say the Cl minus is actually going to deprotonate the OH. Okay, so go and take your lone pair, attack H, and then break the bond and go towards oxygen. This one, I think, very simple step, right? Okay, that's how you get rid of the positive charge on oxygen, and that's how you can get this intermediate here. So you're almost done already. Okay, you get HCl as a byproduct, and always look back at the overall equation. Now, the overall equation will give you a bit of clues, and that's where HCl as a byproduct comes from. Finally, step 3. Okay, step 3, just read carefully. Okay, there's a few things happening over here. Mainly the PO double bond, which is this guy, and the breaking of a PCl bond. Okay, we position everything out first. Okay, let's position first. Okay, so we draw out whatever we had in the previous step. I'm going to draw all the Cl bonds actually. Okay, because we need to show a bit of arrow movement over here. 1, 2, 3, 4. Okay, and they said something about how nucleophilic attacked by another Cl minus. Let's just write another Cl minus here. And we are going to get a few things. Okay, number 1, you need to get the final product. That's for sure. Right, the final product is here just bonded to a Cl. You're gonna get your POCl3 also. Okay, these are whatever you have so far. Okay, let's just do this. Okay, so another Cl minus ion attacks the carbon atom. Which carbon atom? This Cl minus, what carbon does it attack? It obviously has to attack the carbon here, right? Because this is the carbon that's going to bond with the Cl at the end of the day. Just point towards there. And then next. Okay, the next is PCl bond is broken, right? Okay, I'm just going to break this PCl bond. So that's how you're going to get a Cl minus ion here as well. So the Cl minus and Cl minus here will cancel out. Okay, that's why you don't see Cl minus in the overall byproducts. Okay, and finally, it's the PO double bond. How do you form this PO double bond? Phosphorus bonded to 3 chlorines. Okay, yes, 1, 2, 3. This one gone already. Okay, so I need to form a double bond here, right? And where does the electron come from? It can only come from this bond here, right? Because you can see that this is broken at the end of the day. So once this is broken, I'll just transfer the electrons to this bond. I'll point to the bond. That's how you can form the double bond there. Okay, so that's how it works. Okay, you don't need to break it already, then form the double bond. Just transfer the electrons straight away. It can be reached. Okay, so just go and reach it over like this. Okay, so that's the answer to this question. 3-mark mechanism, I think doable. Okay. Okay, I want to talk about part 2. Okay, part 2 is 2 marks. Okay, it's not a simple 1 mark suggest question, so we need to put a bit of time into it. Okay, so as I gave you guys a few clues just now, consider the bonds formed. Okay, so you need to choose something quite significant, not just any random bond that's formed over there. And you must ask yourself how that relates to a very favorable reaction, a very complete favorable reaction.
This borders the line, the concept of energetics, right? Energetics, how do we link it up together? Because bonds form, you link to energetics. Okay, first, what bond is formed over here that's very significant to the reaction? What's the most significant bond form? Look at the product. Okay, what's the most significant one here? Okay, here, right, should be your PO double bond. The PO double bond is a very, very strong bond. How does a strong bond form contribute to the other things? Okay, so let's just write down first. Okay, a PO bond is formed, which is very strong. You want to quote some other bonds also can, but nothing is as strong as your double bond. Okay, so PO bond is formed, which is very strong. Okay, and what does that lead to? A very strong bond means this energetics, right? The delta H of this reaction is very what? Very negative, very exothermic, right? Because it's always bonds broken minus bonds formed. So if the bonds formed is very strong, you're going to get a very exothermic reaction. Okay, so the delta H of reaction 1 is highly exothermic. I'm trying to bring out the idea that this guy is very strong. Guys, think about it. If you have a very exothermic reaction, what does that mean? We talked about this before. We are slowly leading towards a very complete reaction. That idea. A very exothermic reaction means what? The product is very stable, right? A very exothermic reaction, that means the product is very low. Low energy level is very stable. So we can talk about that also. Hence, the product of reaction 1, the products of reaction 1 have very low energy level. You can talk about that also. Have a low energy level, making it very stable. And guys, if the compounds are very stable, what does that mean? Is the reaction going to be favorable? Of course not, right? You form very stable things. We like that, right? Okay, so if you form very stable compounds, the reaction is very favorable. You can just bring out that word. You can paraphrase, okay? It's like paraphrasing your GP like that, okay? Instead of writing completion. Okay, reaction is favorable and it goes to completion. Okay, you are adding value instead of just copying down the last part of the question. Okay, this answer isn't really found in the answer key. Okay, they gave another answer which is also acceptable. Okay, but the main part that is definitely there is your PO double bond highly exothermic reaction. I think this makes sense also. Okay, very stable compounds are very likely to be formed. That's why reaction is very complete. Okay, but just now I did mention another word. Other than the word favorable, a very complete reaction is very what? It's like S. A very spontaneous reaction. And spontaneity, you can talk about what? What measures spontaneity? Delta G. Okay, so if you want to talk about that, can also, but I don't expect you guys to all manage to see that. That's what they came out with in the answer. So let's write down the alternative answer also. Highly exothermic. Okay, if the delta H is highly negative, okay, we can write it here also. Remember delta G, right? Delta H minus T delta S. A highly negative reaction. The delta S here is also positive because you're forming a lot more products. Okay, but again, I don't expect you guys to work this out. Okay, that's why the delta G is highly negative. Now, if the delta G is very negative, right, what does that mean? Very spontaneous, right? And very spontaneous means okay, this is what the answer key mentioned. The Kc is also very large. Okay, again, I don't expect you guys to write the word Kc because it is not technically an equilibrium, but it's just a very, very favorable reaction. So a very favorable reaction has a very large Kc usually. Okay, so they link delta G and Kc together because there's a bridge of spontaneity. Very spontaneous means the forward reaction is very, very favorable. Again, I think this is not a wrong answer, but I just didn't think of that first. I don't think it's very obvious compared to the first answer. Okay, so perhaps you can take both down. Okay, let's look at the final answer here. Part 3 very fast one. What's the intermediate? What functional group is it? Okay, Cn, that's the only answer there. Okay, why Cn? Why not OH? Why not a lot of things? Okay, because step up reaction. Again, it's synthesis, just count carbons. I'll tell you so many times already. Okay, count the number of carbons. There's an extra carbon here. Okay, so just go and add a Cn. There's only one way here, nucleophilic sub. Okay, just go and check your radians and conductance. Okay, so first one is ethanolic KCN and heat. This is the easiest 3 marks of your life or series. Okay, ethanolic KCN and heat, and then step 3 is hydrolysis. Okay, synthesis is the easiest marks to get in organic. Yeah, I say first. Okay, please allocate more time to that in the exam. Let's say you're running out of time or whatever. Okay, can?
How do you identify the pure bonds.
Because they asked us to consider the bonds form. Then you look at the bonds form, right? What's the most significant one? Okay, this PO double bond. No. You can talk about other bonds also, but you must make a mention of PO double bond. You can talk about HCl, you can talk about CCl, yes, but nothing is as strong as PO double bond. Yeah, okay, so you must minimally mention that in your answer. You can mention the rest as well. Whatever. Okay, can? Okay, okay, I don't think I want to do part C. I don't think we have time for that. Okay, because I still want to do another question from later. Let's see. Okay, guys, can you go over the question 3 first? So we settle this okay question, and later we try another one. Or do you guys need a break first? I need a break first. Okay, maybe after this, this question not say very tough as well. Okay, I want you guys to look at question 3 and do A, B, and C. D you can do yourself. Okay, so A, B, and C. It's a lot of writing, not much calculations. Okay, perhaps we take about 12 minutes or so. Okay, 3A to C. Right, after this, then we take a break. You don't have to announce, you don't have to draw all the PCL bonds. Just the ones involved, yeah, can also. I prefer drawing everything out now. Yeah, something.
Yeah, good. If for part C, they never ask you guys to like write balance equations or whatever, so don't waste your time doing that. If just fulfill whatever the question asks for, they ask for what E naught cell observations, just write those two. Okay. If H2O2 can be either oxidized or reduced, just choose the one that works. Okay, so consider both first, but only one will work. Okay, about 5 minutes left.
We need to consider the one because
Consider water local. Yeah. Water is only considered for electrolytic cells, where the selective discharge. Here is just predicting reactions. Yep. pH what? pH is not observation. You can't see pH. This question is about vanadium, got color. Vanadium is a transition metal, all these got color. Okay, we have 2 minutes left. Right, try to move on to the final part also. The final part is like doing the same thing now, right? Alright, time's up. Okay, come. I wrote the answer for part A on the board already. This is the only reason, okay, why it has variable oxidation states. Okay, but I'll talk about density. Okay. Highlight in the question, they said density is significantly higher. Okay. Significantly means, okay, there are multiple factors that contribute to why the density is way higher. Okay, take note of that first. Okay, so when it comes to density, right? Okay, you guys need to first ask yourself the formula of density, which is mass over volume. But again, right, okay, you got to study your notes. Okay, this one should be fine. Okay, so if you want the density to be significantly higher, that means the mass of vanadium has to be larger and the volume has to be smaller. That's how it becomes super high. Okay, can see that first? Okay, when we talk about mass, what do we talk about? How do we discuss mass? Why is the vanadium mass higher? Okay, look at the data because of relative atomic mass, right? Okay, that one very simple. Okay, relative atomic mass is higher. Okay, good. The key thing in this question, right, is your volume. How do you explain that vanadium's volume is smaller? Okay, so this one requires a few things. Okay, you have to look at the tables data over here. You can either talk about atomic radius, but you still need to justify why. Okay, I know it says over there. But there's another more significant reason, and it's similar to the reasoning that we saw in the first part. Okay, and it starts out with this again. 3d and 4s electrons, right, have very similar energy levels. And because of that, right, okay, I'm going to use this to explain another thing. Okay, I'm not going to talk about removing 3d electrons, but now it is about contributing to the delocalized electron cloud. Okay, so let's take a look. They're both metals. Metals have C of delocalized valence electrons. And now they have 3d and 4s, right? Okay, they will both contribute to that. Okay, so hence, since they have close energy levels, both 3d and 4s electrons can contribute to the C of delocalized valence electrons. Okay, that's what we have in metallic bonding, right? And take note, is C of delocalized valence electrons. This is very important. Only the valence electrons, right, can be contributed to the delocalization. Okay, only the valence electrons. Okay, so what am I getting with this? Okay, if it has more electrons in the C of delocalized whatever, what does that mean? The metal has stronger bonds, right? Okay, so you can now tell me, vanadium has stronger metallic bonds, and how does this link towards volume? Okay, if you have stronger bonds, what does that mean for the atoms? The atoms are packed more closely to each other, right? Okay, because stronger bonds, they can hold the atoms closer to each other.
Okay, so you have stronger metallic bonds and its atoms can be held closer to one another. So that's actually another reason on top of the smaller atomic radius why their volume is so small. This question talks about the word significantly higher. So the atomic radius alone, unfortunately, is not enough. Okay, so if its atoms are packed closer together, its volume is smaller. Okay, and you can also say together with the higher atomic mass. Now I talk about the mass. Okay, together with the larger AR of vanadium, then you can now conclude both factors will contribute to a very high density. Okay, density of vanadium is much significantly higher. Quite a long question. They give you a lot of lines as well. Okay, so take note, for density are actually not that easy to explain. Atomic radius alone is correct, it contributes to it, but it's actually not as significant as the stronger bonds. Stronger bonds pack closer together. That's the main reasoning for density. I'll just take note from now on. Okay, Ken? Okay, I will now talk about how you're going to solve part C, okay, very efficiently. Because as I mentioned just now, some of these species, right, can either oxidize or reduce. Very annoying, right? So just consider both possibilities. Okay, so guys, let's look at C part 1, it's a bit easier. For C part 1, again, H2O2 can either be oxidized to oxygen gas or it can be reduced to water. We have to consider both of these equations and let's just write down the E naught values first. Okay, the E naught value for this one is 1.77 volts, very, very willing to reduce. But for oxygen, right, it's only plus 0.68 volts. Okay, but this is oxidation. Okay, again, we will not know which one it undergoes until you look at the other guy. Okay, the other guy is VO2 plus, the one with +4 oxidation state. Again, this guy, right, can either oxidize to a higher state, which is your VO2 plus, or it can reduce to a lower oxidation state, which is V3 plus. Okay, go one by one. Okay, well, let's go and check the E naught values here. Okay, this one is 1 volt. Okay, V3 plus is what? V4 plus to V3 plus. Okay, so we need to check everything. Okay, so plus 0.34 volts. Okay, so with these two values in play, right? Okay, now we have to see which pair makes sense. If H2O2 is oxidized, that means VO2 plus must reduce. Now, reduction minus oxidation, does this work? No, okay, this doesn't work, so we can strike off both of these guys already. Strike this off, strike this off, so it must be this and this. And does it work? Reduction minus oxidation, yes, you get a positive value, so you choose this pair instead. Okay, so with that said, okay, you just write down your E naught cell. That's one thing that they ask for you guys. So 177 minus 1 give you positive 77. But again, go and tell me, it's more than 0. Okay, so it's spontaneous. This part 1 mark. The second mark, don't even need to write equations or whatever. The second mark is to tell me your observations. Okay, what do you see here? Okay, go and refer. Okay, guys, I told you before already. Vanadium no need to memorize colors. Chromium you need, copper you need, yes. Okay, but vanadium they will give you. Okay, so over here I started off at VO2 plus and I've now oxidized to VO2 plus. Okay, so what is the color shade? Okay, good. Okay, it's not blue to yellow. Okay, they accept blue to yellow now. But there is an intermediate color in between now because as I mentioned, this reaction isn't instantaneous. It happens over a course of a few hours or maybe even days. Okay, so there'll be an intermediate which is a mix of both of these guys. Okay, so yellow and blue will give you green. You need both of them. Okay, so the solution turns from blue to green to yellow. Acknowledge the mix of colors. Okay, 10? 2 marks. Okay, then let's see why the next part is more than 2 marks. Okay. Okay, as you can see first, let me mention one thing. From VO2 plus to VO2 plus, this guy's oxidation state is +5. Can it go any higher? No. Okay, vanadium is max +5. Okay, so we'll see how this comes in later. Okay, let's do the same thing. Okay, for VO2 plus, you can either oxidize to a higher state, look at the E naught value, or you can reduce to the lower state, which is 0.34 volts. Okay, and then next for tin. Okay, guys, go and find tin, and you realize, right, this guy can only oxidize or reduce. Okay, from the data booklet, this guy can only oxidize to SN2 plus. I know there's a SN4 plus, but that one doesn't involve tin, the metal. Okay, so what's this value over here? Okay, this value here is negative 0.14 volts. Okay, so if this is oxidized, you only have one choice here. Okay, so if this is oxidized, you can only choose the reduction pathway, which will still give you E naught more than 0. Okay, so E naught cell is 0.34 minus negative 0.14. Okay, you can get 0.48 volts, more than 0, reaction is spontaneous. Okay, so on and so forth. Okay, what's the observations you see here? Okay, you have reduced your VO2 plus to V3 plus. Check from blue to green. Is there any color in between? Okay, no. Okay, blue and green, you will just see bluish green in between, which you don't need to mention. Okay, so if there's no intermediate color, you just tell me blue to green. Okay, so first of all, the solution turns from blue VO2 plus to green V3 plus. Okay, so currently I only have 2 marks. Okay, one here, one here. How do you get the final mark? Okay, how do you get the final mark? What must you also check? Okay, we mentioned this before. Okay, just now how I said this, right? V4 plus, okay, 4 plus to 5 plus, that's the maximum it can go. But here is the minimum it can go from 4 plus to 3 plus. Can it still go even lower? Right now we don't know, right? So you need to check. So guys, every time there's this kind of vanadium questions, you've done this many times, right? You must check whether it can continue the reaction. So the keyword in this question is excess tin. You're going to still have tin left over. It can still further reduce this if possible. So what you need to now check is whether V3 plus can reduce to V2 plus. Is this possible? Okay, so go and check whether this reduction is possible. Okay, the value here is negative 0.26 volts, right? You are still going to use tin, and is this possible to reduce? Okay, is this possible? No, right? Okay, reduction minus oxidation, you give a negative value, meaning to say the reaction actually stops in the first part. But you need to still mention it. You still need to check the next step. Why we never check here is because +5 is the max rate. Okay, so we check over here now. Okay, so now the E naught cell is reduction minus oxidation. You get a negative value less than 0, not spontaneous. Then you give me a statement also. Okay, what does this value represent? Okay, this tells me that V3 plus does not reduce further to V2 plus. This is your final mark. Okay, I think we tend to forget this because it just doesn't, if it doesn't happen, we tend to forget. It's quite normal. Okay, but just from now on, check vanadium, just try to go as far as we can. Right now, the furthest I can go is only 1 step. Okay, but the next step stop me already. Okay, always must give me the ending, which is when it turns not spontaneous. Okay, enough. Okay, the question itself is not demanding because they never ask us what equation this one, that one. Okay, so it's quite okay. Right, Ken? Okay, all good, Right, okay, perhaps, right, okay, we take a short 5-minute break because we still have one more question that I really need to go through. Okay, we take a break first, 5-minute break. Then later we do one final question. This is the other set. Okay? Yes. Okay, we have got one question from now. So how do we know which tin equation to use? Okay, take note now. The tin equation to use is tin to tin 2 plus, because if you find from the data booklet, right, there is only tin to tin 2 plus. They give you tin, so you must find tin. There's only one equation with tin metal, which is tin to tin 2 plus. Make sense? Okay, you don't use tin 4 plus to tin 2 plus because that one doesn't involve tin metal. Got it, right? Okay. Yes. How was it? Okay.
I don't know what's the region. I don't know exactly.
Because if you had H2O heat, right?
Yeah.
You will also deprotonate. You also protonate the amine, right? Is that a capture?
Yeah.
Yeah. Okay. So usually, right, the H2O heat is either in a controlled manner. So such that, right, your other guy doesn't. Okay, because if you realize, right. Yeah, you just have to edit the control panel. If you add whack, then everything will end up so control addition of H2SO4.
That will be safe. That will be safe.
We got live, bro. Let's go ahead, go ahead. Go to first on this. You want to? What? No, you want? I don't know.
Next week, you have to go through the prelim paper and all that. Right. Okay, but haven't arranged it. So maybe like this Sunday, should see also then or maybe I'll just text you guys. Next week, maybe one of the days you prepare a prelim paper first. Yeah, and you just ask me everything in that next week's session, 2 hours. Make sure you ask everything. Yeah, and then whatever other stuff, other papers you have also just ask me during that table. Yeah, that'll be better. Probably sometime next week. Yeah, see when. Check for the users. Okay, guys, we have to continue first. Okay, we're gonna end soon. Okay, but after this question, I think this is an important question. Okay, so can you guys, sorry. Yes, okay, can you guys take out the other set that I gave you guys? Okay, it's not set. Okay, the title is set 6. That's not set 6. Okay, you might want to cancel that and write that extra worksheet or something, extra revision. Don't be confused. I'll go and change it. Okay, but then for kind of printed the wrong copy also. Yeah, okay. Go and take out the other worksheet, just change it to extra revision 1. That one this can be found in the Google Drive as well, but it's in the other folder, so I don't want you all to get confused. Okay, call this extra worksheet or something. Okay, so yeah, this one, there are some questions here you guys can go and revise also, go and try yourself, but today I'm just going to focus on one particular part, right? Okay, so can you guys go to question 2? Okay, the extra set, question 2, and I want you guys to try A part 1 and A part 2. Done. A part 1 and A part 2. Yep. Instead of condensation. Yeah, because carboxylic acid and acid, AB is a base. You just instantly react together. It does have a higher chance of forming. Like they actually do it in real life, then they realize that that's what happened instead. Yeah. Chances of it, I think, is a nucleophile much lower. It doesn't happen. Yeah, that's why I use acyl chloride, because we mentioned in the last lesson, acyl chloride is an acidic. It's only after you add water, it produces an acidic solution. But the compound is not acidic. That's why it can force the nucleophilic effect better. It's a higher chance. Okay, A part 1, A part 2. Don't spend too much time on A part 1. Okay, that one is just a suggest question. Okay, A part 2 is where it's at, right? Okay, give you guys about 6 minutes for this, okay, should be more than enough time. Okay, for part 2, they ask us use the PKB value. So just legit compare the PKB values and ask yourself what they mean. If one PKB value is larger than the other, what does that mean? Right, okay, so try that. Okay, and stare at the equations. These are equilibriums for a reason. Okay, about 2 minutes left. You also got to ask yourself what's the meaning of a living group, right? What does it mean to be a good living group versus what does it mean to be a bad living group? Okay, so you compare what's good versus what's bad. Okay, then you get a better idea of what it means by a poor living group, right? This question is familiar. Either. Okay, can I go through the question? Okay, right. Okay, so it's not meant to be an easy question, okay, but I think it's a very good application, right? Okay, they introduce this idea of living groups. Now, living groups is like technically it's not really in the syllabus, okay, but they have covered it quite a bit, and then they usually teach you guys in the question. So again, it is entirely possible for A levels to come out with this idea of living group also. Okay, so let's look at this question now. Okay, so first of all, they are saying that okay, the nucleophile attacks this, and then they undergo some sort of reaction over here, right? Okay, to form that. Okay, basically, a living group is something that leaves, right? Okay, it has left the acyl chloride derivative over there, okay, and then it's replaced with a nucleophile. Now, the question has given us this statement. The stronger the base, which is a living group, the poorer it is as a living group. Okay, so what does this mean? What is a living group? A living group is something that leaves, right? Okay, so if you are a poor living group, what does that mean? Or perhaps, right, okay, let's look at the other way first. What does it mean to be a good living group? A good living group is something that leaves and does it come back? No. See these reversible arrows here? Okay, it implies that the backward reaction could happen. So if you are a poor living group, that means you leave already, but there is a high chance it will come back. Right, okay, so perhaps you can break this down. A poor living group is something that leave already, right? But probably will come back. That's a shit living group, right? Okay, a good living group is something that leave for good. But this is bad. That means it will probably come back to the compound, which is what? You're going to reverse the entire reaction, basically. Can you all see that? This living group over here, right, can actually reverse and come back. Why would we want that to happen? That's a terrible thing to happen, right? Okay, then, but the thing is why? Okay, let's try to make that link over here. What does a strong base mean? Okay, they say base. A strong base means what? We talk about basicity so many times. Okay, a strong base means the lone pair is very available, right? They even draw the lone pair for you. Okay, so let's just write down whatever we know first. Okay, the stronger the base, the more available the lone pair of electrons for donation. Okay, this is whatever I know first. Okay, so if the lone pair is more available for donation, that means it's gonna be what? Okay, take a look at this. A poor living group is something that comes back. It's something that reverses the reaction back here. How does this reaction go backwards? What would this lone pair do? It's more available, right? So it is very likely that it can do what? It can attack the guy again, right? What's stopping this from attacking the guy again? Right? Nothing, right? He is very likely to re-attack this guy. And when he attacks this guy, you're going to break apart the nucleophile and then you're going to go back to the start. So you're going to reform the starting compound. Basically, you just wasted your time. Okay, so over here, if you're more available for donation, hence, it is very likely for it to attack the electron deficient carbon atom. Okay, reforming the starting compound. This is the main part you need to write. If something comes back, that means he doesn't want to leave, right? Okay, it's a very bad leaving. Right, okay, not saying it doesn't want to leave, but it leaves first, but then it reverses back. There's a high chance for it to reverse back. Okay, so you can tell me that's why it's a poor leaving. Can I see that first? Okay, so yeah. Okay, let's take a look at the second part.
Okay, this second part over here, they ask us to only do one thing. Go and look at the PKB values and tell me why 1 is better than 2. Okay, why is this the preferred reaction? Okay, so again, you look at the table here, the PKB values are used to look at the leaving groups. And you can see all these leaving groups appear in both equations. So again, let's just write all the PKB values down. This guy PKB -2, this guy PKB 9, this one -2, this one -24. Okay, so come, let's compare. This is a POE, a reversible reaction. What does it mean? Okay, let's just break it down first. This guy versus this guy, what do you notice? The lower PKB means what? This guy is the stronger base, right? In comparison to each other, relative to each other, this guy is the weaker base. What does that mean? Who will dominate? The stronger or the weaker base? Obviously, the stronger base, right? Okay, the stronger base will dominate over the weaker base. So essentially, the stronger base is going forwards. This base is going backwards. So at the end of the day, what's the net direction? Forwards, like. Can see that the stronger base will be stronger for a reason. That's why the extent of his dissociation is much larger. That's why the POE is now facing the right, which is exactly what you want, because I want to form this product. Now you look at the other side, guys. Over here, compare now. What do you see when you see these two bases? This guy is now the weaker base, right? The smaller PKB is the stronger base. Now, in turn, this guy ends up being the weaker out of the two. So what's going to happen here? The stronger base, which is now on the right-hand side, will dominate, right? So now his dissociation is more towards the left. Okay, the left will win the right because it's stronger. So now the POE on net direction is facing the left. Do you want it to face to the left? No, because this question wants you to synthesize methyl ethanoate. I want this, so of course you want the POE to shift right. But the second reaction, the POE is actually lying towards the left. Okay, so all you need to compare in this question, PKB smaller. So he's a stronger base than this guy. Stronger base means the POE of this reaction lies towards the right, hence synthesizing methyl ethanoate. On the other hand, this guy, the stronger base is now him. So now the POE will lie towards the left and you don't synthesize methyl ethanoate. That's it for this question. You can see that stronger will always dominate than the weaker one. Can see that so far? Okay. So yeah, if there are no questions here, that's it for today. Okay. Yes.
Can I say that this is like that the carbon in the center would be more electron.
Yes, it's an electron donor, but we're talking about a stronger electron donor. How does a stronger electron donor contribute to
carbon more electron rich, so the neutral power will be less likely to attack the carbon.
How does making the carbon more electron? Okay, it's not rich in the first place. Okay, so
less electron.
Okay, so it becomes less poor, so it's less likely attack. Okay, so you're now talking about the carbon, right? No, the carbon here is the same poor, right? No matter what the leaving group is. It's equally poor no matter what leaving group you use. Here, the focus should be your leaving group, not the carbon getting attacked. The carbon has an equal amount of chance getting attacked by anything. It is just the chances of this guy doing the attack. Because we are talking about the leaving group, which is this guy, right? A stronger base means it's a higher chance of attacking. Not about him, higher chance of getting attacked. You can see the difference here. You're supposed to be talking about this guy, not the carbon. Yeah, so maybe tune your answer a little bit more, right? Then yes, you can get the full thing already. Yeah. Okay, again, if you have no more questions, right? Yeah, that's it for today already. Okay.